Okay, prepare yourself because everything I say today is going to be super, super, super theoretical. There are a lot of equations involved. Please do not try to write all this down. Go back and look at the slides that have all the equations on them because there's a lot of getting from point A to point B. And you won't need to use anything in the middle. So it's hard in this class because there's a lot of stuff that is mathematical and statistical that goes into determining how we figure things out. And it takes us all of the beginning of the course just to get to where we can figure out how we have charge carriers. And that's the first 3 chapters of the book, is figuring out how we know what we have. So today's is probably the most theoretical and difficult lecture that I will give you, but it is not something that you need to be afraid of because you're not going to have to use most of the math that's in here. Part of it's necessary because if we just go to the end and I say this is how you figure out how many electrons you have, you won't know why. And there's a big part of what we do of the why that actually makes a difference. So last time we talked just a little bit about quantum mechanics from the beginning, and we talked about kind of how it came about. And we really didn't talk about the details of it, we just did some kind of general overview. And we're going to talk about enough details of it for you to probably just get confused, which is fine, because as all the physicists said, you're not expected to understand it. If you think you do, you don't. So don't worry and get stressed out when you see all the math, because there is quite a bit of it. The first thing we're going to talk about is something that we won't have to deal with in 4 dimensions, but it's something called the wave function. The wave function, in all its glory, has 4 dimensions because space has 3 dimensions and time has another one. And if you were going to fully describe a wave, like a light wave or an electron, you would have to describe it in 3 spatial dimensions and 1 time dimension. And that is really, really, really theoretical and generally figuring out what one of these equations would be for in 4 dimensions would be way beyond the scope of the course. But it does exist, and we use kind of a sort of a part of that. We actually narrow it all down to just 1 dimension and no time, which makes it a lot easier. But first of all, we have to start with what we want to know about an electron, because everything in semiconductor devices depends on the movement of electrons, either electrons in the conduction band that are moving freely or electrons in the valence band that are moving from empty spot to empty spot and basically making holes move. So what do we want to know about electrons in semiconductors? Well, we'd love to know where they are. We can't. We can know where they might be. That's the best we can do, is try to figure out where they might actually be. So any individual electron, we can't ever tell where it exactly is, but we can theorize about where it might be. The other thing we would like to know is what does its wave function look like? And you can come up with all kinds of things that it might look like, and we're only going to come up with kind of one. And then how much energy does it have? How much energy does an electron in a particular thing have? Because basically there are states in which the electron can be, and it can be at different energy levels. So basically where it might be and kind of how's the wave function working and how much energy does it have, that's really all we can know about it. So most of what I'm going to talk about for the next few minutes is just about energy, and just energy by itself. So all the energy in any system has to be conserved, and we all know that. We talked about that before. And the energy is always going to be some kind of combination of kinetic or moving energy and potential or energy that could move but isn't right now. So that combination of energies goes into determining kind of how we figure out where an electron might be. So before we start talking about the wave equation in one dimension, we're going to talk about one dimension plus time for a little while, and then we're going to get rid of the time eventually. So the general form of the wave equation, if we're talking about an electron and in time dependence, has this e to the I and then a whole bunch of stuff in parentheses, kx minus omega t. That's just the Euler form of a complex number, if you remember that, with a magnitude of 1. So there's a 1 in front of the e, and then everything else, if we were to plot it, it looks like a circle, but there's a phase angle, so it's a point on this circle, basically, some point, and the phase angle is equal to kx minus omega t. So those two things go together to kind of determine where that might be. Is that useful? Not yet. So in order to make this easier, we're only going to look at the x part. So if we do anything like take the derivative or the second derivative, which we will do, we're going to treat time as a constant like everything else. And we're just going to look at the place, basically, where it is. So if we just look at phi of x, that's just a time-independent wave function, and that describes the behavior of electron in a crystal, which is what we have. That's the whole reason why we have it, is because it describes directional motion in a crystal in one dimension. And we're not going to look at 3 dimensions. I mean, there are 3, but we're just not going to worry about that part. So we're going to go through to try to figure out how to use this to figure out how much energy there is. And we're going to have to look at, first of all, the fact that total energy is potential energy plus kinetic energy. We all know that, which is good. In here, frequently, potential energy is symbolized by a V. That's because voltage is a type of potential energy. All voltage is potential energy. If you have a circuit and you have a voltage at a particular point, that's just an amount of potential energy that's going to be lost as current travels through the next element that causes it to lose energy. So voltage is just a type of potential energy, and all potential energy that's relating to what we're doing today will be symbolized as a voltage. Kinetic energy, if you've been exposed to this before, is just 1/2 mv squared. So that's something that if you had physics ever, that was discussed relatively early on in the course, usually when you're talking about mechanics, and pretty soon talk about 1/2 mv squared is the kinetic energy. In this case, because the kinetic energy is going to be of a particle that is moving, we're going to substitute momentum equals m times v into that equation. So we're actually going to have rho squared over 2m. That's the same thing. All we're doing is looking at the momentum, combining the mass and the velocity, rather than looking at the mass times, because we can't measure the velocity. We can actually look at the momentum some, but we don't measure the velocity. So the energy of a particle now looks like V, whatever V might be, plus rho squared over 2m. So we're going to set that aside for a minute. Just whatever voltage exists, and then whatever momentum squared over 2 times the mass. Now we're going to do calculus for a minute. And we do that from time to time in here. And we're going to do calculus on the original wave function that I just showed you. And the nice thing about calculus on an exponential is it's really, really easy. You remember that when you take the derivative of an exponential, it's basically just what you just had times whatever is in the exponent that is part of the dependent, part of the, this is why 630 classes are difficult. Whatever. It's the variable. There we go. At least I didn't forget the word semiconductor today. Sometimes I do. Anyway, we're going to take the first derivative of that, e to the I kx minus omega t. And we're treating omega t as a constant. So the only thing in the exponent that is really related to the variable would be I times k. So when we take the first derivative, we get ik, and then we get our original wave function back, basically, because that's part of the exponential. So we got an imaginary number, but that's okay, because we're going to take the second derivative and get rid of the imaginary part. So we're going to take the second derivative of the same thing, and when we do that, we get I squared k squared, and then the wave function again, and I squared is just -1, so we get negative k squared phi. And you're sitting there, okay, what is that k thing in the middle there? What does that even mean? And where are we going with this? Well, k is actually related to something we did last time. It's actually called the de Broglie wavelength. Remember that Louis de Broglie figured out that electrons were waves, and he came up with a relationship between momentum and Planck's constant and all that. And it's defined as the momentum divided by something called h bar, which is just Planck's constant divided by 2 pi. That's all that is. It just makes it easier for the calculation part. So, the second derivative, we can substitute in and get minus rho squared over h squared phi. And then we can move things around just a little bit and get that. Do we have to use this for anything? No. We just have to use it to get to the next thing, but we don't actually have to use it for anything. That's why I was saying don't bother trying to write all this down. You can go back later and look at it. It's all on D2L. Okay. This is where we're coming to the kind of conclusion of the derivations. So, E is rho squared over 2m plus phi. If we multiply everything by phi, the wave function, we get E phi equals rho squared phi over 2m plus v times phi. Then we can go and substitute in that second derivative that we did from the previous slide. So remember that back here we had the second derivative was equal to something, and we're actually going to take the second derivative and put it in that equation and substitute it in. And we get this kind of funky looking E times phi is equal to minus h bar squared over 2m times the second derivative of the wave function plus the voltage times the original wave function. That is a second order differential equation, which I'm sure you probably haven't had yet. Maybe you have, depending on when you're taking this course, but that's what that is. And the question is, are we really going to have to use this for something? In general, no, not really. Sort of. We are going to use it to go somewhere, but no, I'm not going to make you solve it. If you were a PhD double E person, yeah, you probably would have to solve it. And people go around solving for different waveforms all the time, but you don't have to because we're a very specific case of the wave function. So, this is known as Schrödinger's wave equation. The guy who was sorry he had anything to do with quantum mechanics. He developed this equation to describe the momentum or movement of electrons. And basically, what this is saying is the total energy is equal to the potential energy plus the kinetic energy. So that's still contained within that equation. If you happen to have a form of the textbook, either the one that is the present edition, it's presented slightly differently there, but it's almost the same. It's moved around some, but it's the same equation. It's exactly the same. You get the same numbers. It's just taken it and it's just moved things around. That's all it's done. So why do we care about all this? Why do we care about this wave function to begin with? The reason is the position and energy of a particle can be found in terms of probability, and probability is directly proportional to the absolute value of the wave function squared. We're going to look at electron energy. We're going to kind of use this equation to get there, but we have to have it in order to figure out where electrons are. So we kind of have to use it. So the energy of an electron depends on how far away from the nucleus it is. If an electron has negative energy, so if you do a calculation and you come up with a value and a number for energy and it's a negative number, that means it's bound to a nucleus. It's actually part of an atom or structure. If you have an electron with positive energy, that means it's free. It's got kinetic energy and it's moving somewhere. That's the positive energy. The simplest model we can use of an electron is the electron around hydrogen, because there's only one. And electrons can exist in hydrogen at different energy levels, but there's only one of them, so that makes it just a little bit simpler. We talked only briefly for a minute about the Bohr model of the atom, which comes up in chemistry, and the Bohr model of a hydrogen atom states or predicts that there's a certain distance from the nucleus to the electron that exists in hydrogen. So that was figured out well before quantum mechanics was started. So how does that distance, since the Bohr model says it's here, and we know it's not really there, we know it could be there, but it may not be there, how does that fit together? How does that value, which is supposed to be the distance of an electron to the nucleus, fit with the fact that we know that it's not going to be exactly there all the time? It could be somewhere else. Well, this is how it gets resolved, and this is where I need to do more math. So let's pretend we have an electron, and we have a nucleus and a distance from the nucleus. So the electron is a distance r from the nucleus. Yes, I know, it's theoretical. The potential energy, there's like two things going on. First of all, the electron is moving, so it has velocity, and then it's also being attracted by the nucleus. So it has a velocity vector and a force vector, and both those are working together. And no, you don't have to add vectors in this class either. I just like using them because they're convenient. There's only two charges. There's like an E and a minus E in this. They have equal charges. So basically we can figure out the potential energy of this situation, and we get Ke squared over R. And K actually does, I told you it was momentum over, but it also has a way of being calculated by just using 1 over 4 pi times the permittivity of free space. I believe it is. So we can actually come up with a way to figure out what the potential energy of an electron is if we know the distance from the nucleus, because we know the charge of an electron is E. We know 4 is equal to 4. We know pi is equal to pi. And then the permittivity of free space is a constant that can be figured out. So it just depends on distance, and that's it. So we can figure out, and this is actually presented in your textbook as the magnitude, taking magnitude of the electric charge over the permittivity of free space, the radial distance between the proton and the electron, times 4 pi, and do that equation, and you will get the potential energy of the electron. So that's about half of what we need to know about the total energy. We can figure out the potential energy pretty easily, just depending on how far away from the nucleus it is. Kinetic energy of the same thing, that's where you get KQ1 over Q2 squared, R over R squared. That's where you get the kinetic energy. So it's a little bit different. And kinetic energy, that's the force. And then kinetic energy is also equal to 1/2 mv squared. Force also equals mass times acceleration, which I'm sure you get that in physics as well. So what we can do, because we know that this thing is moving in a certain way, we can actually replace the acceleration with v squared over r. And we're going to get yet another equation, me, which is the mass of the electron, v squared over r. And we're going to cancel r in the denominator and multiply y1/2 in both sides because we want to put this into the form where we can get the kinetic energy. So we want somehow to get 1/2 mv squared on one side so we can figure out what the actual kinetic energy is. And we get 1/2 ke squared over r is actually going to be equal to the kinetic energy. So now we can put them together, and it looks really similar, actually, in a way, to the potential energy. And we can put those together, and when we add them all up, the energy of an electron going around that circle is minus 1/2 ke squared over r. Now, what we're going to do is we're going to do a massive amount of substitutions into this equation because it's just not simple enough. K is a conglomeration of a large number of factors. The radial distance is a conglomeration of a large number of factors. And so we're actually going to substitute in all those because they're all related to each other. So in other words, the radial distance is related to the quantum number times h bar, which again is a constant, over the mass of the electron times the velocity. So we can take that r and kind of, because we can't go out and measure that. So we have to actually put that in terms of something quantum mechanical that we can actually deal with. We can also take the velocity, which is e squared over 4 pi times the permittivity times h bar times that quantum number again. And then we can substitute k like we did last time. And if we do that, we can kind of do triple substitution, where we take the minus 1/2 ke squared over r, and we can first substitute in the k, so we get the 4 pi times the permittivity in the denominator. Then we can substitute the r, and now we put nh on the bottom and mev on the top, and then we replace the v. And we get this massive kind of equation, but if we have the mass of the electron times electronic charge to the fourth divided by 4 pi times the permittivity squared times 2 times h bar, which is Planck's constant over 2 pi, times n squared, there's only one thing that's a variable. Everything's a constant. So if we look at that, the only thing that really changes is the quantum number n. Everything else is a constant of some sort that has been figured out by physicists in the past and does not need to be figured out again. Which is why I have to go through all that math to get to this point. Because if I just gave you that, you would not know where all that came from. All that mess is just a whole bunch of constants which were derived by previous physicists, and then the quantum number is what ends up being the variable, which makes sense because the electron can only exist at certain energies. So if you figure out that whole mess of constants and then just divide by different quantum numbers, you will get different stable values, and those are the energy places or the energies that the electrons can have. And we're going to look at kind of the energy of an electron later. So this is the only, well, even that, I would not ever ask you on a test to do energy levels like that because it's stupid. Because you'd just be doing a bunch of constants. I have, although in homeworks, asked you to do that. So I can't remember if I did this time or not. I have in the past. So quantum numbers we haven't really talked about a lot, but basically there are a large number of numbers that go into determining the quantum number of something. It's not just the one number. So if we were to take the wave equation again and expand it out so that it's not just x, but it's actually in spherical coordinates, if we do that, we can separate out the functions. We can take it and we can separate it out into three different functions that are three different things that determine where electrons are. And I am actually looking at it in 3 dimensions right now, but not time. So R of R is how far the electron is from wherever it is. And that only can be solved for n equals 1, 2, 3, and so forth. So that value is going to just be the distance. The p of theta is the angular momentum as it's moving around wherever it's moving. And if that is solved, and I'm not even going into what equation that is that's getting solved, but it only has solutions for values of L equals 0, 1, 2, up to n minus 1. So if n equals 1, then you can only have L equals 0 for that particular thing. You can't come up with any other L values that will work because it depends on the value of n. And then the last one is the orbital of the subshell. I don't talk about shapes of orbitals because they're really weird. I mean, the first one is spherical, but then they get like, you got a ball up here and a ball down here and a ring in the middle, and they get really weird looking. But basically, it just describes what the orbital looks like, and that equation only has solutions for m equals negative L up to L. So it depends on L. So there's 1, 2, 3 numbers, n, L, and m. And there's also spin. There's plus and minus 1/2 spin, which I didn't talk about so much, but let's see, where am I? I kind of lost track of where I was. Oh, I'm not nearly as far as I thought I was. Okay. So quantum numbers basically tell you the state of a particular particle. And only one particle per quantum number is allowed, technically, in a particular system, which is going to cause problems later because, you know, we've got like billions of electrons in a system, and how do we deal with that? So we don't have a billion quantum numbers, but that doesn't come up until like next week. So we've got the 4 ways of determining quantum numbers, and we're just going to look sort of at an example of what that would look like. Let's say we have a wave function at the very lowest energy state, where n is 1, L is 0, m is 0. And if we were going to figure out what that value would be, or the value of the wave function for that value, again, we're mostly dealing with constants, but we have A0 as, well, that's where all those 4 pi permittivities, Planck's constant, all those got bundled into that. And that is actually the Bohr radius of the electron. That just happens, all those constants multiplied together equal the Bohr radius that was discovered many, many years ago. So it is part of figuring out where the electron is. If we take that function and we plot it, that function, remember, if we take the absolute value squared, that will be related to the probability of where we find an electron. So that particular, this example of a quantum function, or this example of a wave function, if we actually take it, square it, and we have to do other things to it, but not much, we can get a plot of where we expect to find an electron. And what happens is we end up with a curve. This is the probability distribution of where an electron might be around a hydrogen, in a hydrogen atom. And you will notice that the greatest probability of finding an electron is at the Bohr radius, but it's really only about a 55% chance that it's there. There's other places it can be. It doesn't have to be there, but the greatest chance is that it would be there. So that's good. It kind of lines up with what was discovered, but it can be anywhere in that particular curve, as it were. If we look at the second energy level, and we plot that, interestingly enough, you pretty much mostly have a greatest chance of finding the electron at 5.2 times the Bohr radius, but there's still a small chance that you'll find it in the original spot, even if the quantum number is 2. So these are all probability distributions that are gained from taking the wave function, squaring it, and coming up with a probability of where we find an electron. Electrons in other systems are obviously more complicated because you've got more than one electron. But in any system, you notice that, for instance, hydrogen and helium generally have n values of 1, and the spin can actually be plus or minus a half. For hydrogen. For helium, one of them is going to be minus, one of them is going to be plus a half, because they have to be different. So we mostly don't deal with most of these elements, but this gives you an idea of what the possibilities would be in a regular atom. All that being said, most of the time what we're going to deal with is we're going to model electrons as being electrons kind of like electrons around hydrogen, and then look at what happens when they come together. So, and you'll see that. So I'm going to talk just a second about something kind of unrelated, just to give you an idea of how weird quantum mechanics is with electrons. And then after that, I'm going to say a second sort of presentation about something else. So first of all, every electron has a spin. It can be plus a half and minus a half, and it doesn't. And that's the half doesn't mean that it's half spin or anything. That's just how they determined. Physicists, when they discovered the spin, they just discovered that it can go one of two ways. You can actually take a pair of electrons together. If they're in the same place, they have to have opposite spins. That's what you hope. You can take a whole stream of electrons and send them through an electromagnet and make them all have the same spin. That's something you can do. So you could take a bunch of electrons that some have plus minus a half, send them all through this electromagnet, and have them all come out with a positive spin, positive 1/2. Then what you can do is you can send them through a filter that only allows electrons with positive spins through. So what you would expect is that all the electrons are going to go through because they all have a positive spin. So that's easy, that makes sense. Now what if we take the filter and make it into a negative spin filter? So we get positive electrons, they go to the negative spin filter, and pretty much nothing comes through because they all have a positive spin, and this is a negative spin filter, so it doesn't allow anything through. So far, this is unremarkable, completely. But what happens if we turn the filter 90 degrees? What do you think will happen? Will anything go through? Shouldn't. Well, this is what happens, because they can only have a positive spin or a negative spin. They can't have anything in between. What happens is half of them go through. They actually change their spin because they can only be plus or minus and they can't be anything in between. So because that's a 90-degree filter, half of them come through as a positive spin and half of them don't. Which is not really what you would expect with regular classical mechanics. That's one of the weird quantum mechanics things that happens. What if you change it and you put a different filter on that's 45 degrees?
75%?
Close. It's actually 85% because it's related to cosine squared over theta over 2. So it's a little bit more than 75%, but that's a good guess. And there is actually a very smooth continuum that wherever you change that filter, as it gets closer and closer and closer to vertical, you'll get more and more of them going through. That is one of the really, really weird things about quantum mechanics, because it shouldn't happen that way. Electrons should not be able to do that, and yet they do.